Good morning, students. Welcome back to our Valenzuela live streaming. We are going to have another exciting and fun-filled learning as we discover the world of chemistry. Before that, please take note of the following reminders. This is Lesson 1 of Quarter 2 in the Science module, and the objectives for today are: trace the scientific breakthroughs leading to the development of the quantum mechanical model of the atom, predict the probable location of electrons in an atom, describe electron configuration and write the correct electron configuration of given elements. Describe the set of quantum numbers and complete the given set of quantum numbers for each given element. And supply the following data from the electron configuration, such as period number, group number, number of paired and unpaired electrons, number of valence electrons, and number of core electrons. Now let's proceed to our lesson. In your grade 8 chemistry, you have learned that matters are made up of basic unit called atoms. Are you familiar with this logo? Yes, you're right. We often see it as logo in science. But did you know that this logo is just one of the atomic models designed by one of the scientists who wanted to show the composition and structure of the atom? Several scientists conducted studies about how an atom looks like, and they proposed different models of the atoms. Now let's see if you can still remember them. I'm going to show you a picture of an atomic model, and you type on the comment section what atomic model is it by writing the letter of the correct answer. Ready? Let's start. Number 1. The correct answer is letter A. This model was proposed by John Dalton in the year 1803. Next. The correct answer is C. This model was proposed by Joseph John Thomson in the year 1904. Third picture. The correct answer is D. This model was proposed by Ernest Rutherford in the year 1911. Lastly, the correct answer is B. This model was proposed by Niels Bohr in the year 1913. Good job, students! The different atomic models that you've seen tells us the history of how atom was discovered and how it was studied throughout the years. Bohr's atomic model described the electrons to be moving in definite orbits around the nucleus. Much later, scientists discovered that it is impossible to determine the exact location of electrons in an atom. So, Bohr's idea was rejected. Three physicists led to the development of a better model of an atom. These are Louis de Broglie, Erwin Schrödinger, and Werner Heisenberg. Louis de Broglie proposed that electrons behave as both wave and particle. Heisenberg discovered that the exact location and momentum of an electron at a given time cannot be exactly determined. This led him to the Heisenberg's uncertainty principle. Schrödinger used the idea of de Broglie to develop a mathematical equation to describe the probable location of an electron around the nucleus called the atomic orbital. These three physicists led to the development of the quantum mechanical model, which determines the allowed energies an electron can have and how likely it is to find the electron in various locations around the nucleus. But in order for us to completely describe an electron in an atom, 4 quantum numbers are needed. What are quantum numbers? Quantum number is a value that is used when describing the energy levels available to atoms and molecules. Quantum numbers are important because they can be used to determine the probable location of the electrons of an atom. A total of 4 quantum numbers are used to completely describe the movement of each electron in an atom. Now, in order to find these 4 quantum numbers, you need to keep in mind the following steps. First, start by writing out the electron configuration and orbital diagram for the element. Second, get the last figure in the electron configuration. And lastly, determine the 4 quantum numbers. Let's start with the first step. Electron configuration is a way of distributing the electrons of the atom among the orbitals of the atom. The mnemonic device given in the figure here can be used as your guide in showing the electron configuration of an element. In using the mnemonic device, the direction of the arrow was followed, meaning it starts with 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so on. Does it look familiar to you? Yes, you're right. This looks like a Christmas tree. Take note that S has only 2 electrons. P has 6 electrons, D has 10, and F has 14 electrons. These S, P, D, F are what we call as subshells or sub-energy level. Now let's get the orbital diagram of the element. Orbital diagrams are pictorial descriptions of the electrons in an atom. There are rules useful in forming orbital diagrams. The Pauli's exclusion principle says that only 2 electrons can fit into a single orbital and must have an opposite spin. For example, consider the orbital diagram of lithium. The orbital diagram should look like this and not this one. Hans' rule states that electrons go into different orbitals in the same sublevel before pairing up inside orbitals. For example, consider the orbital diagram of nitrogen. Notice that in 2p, electrons spread out or they go into available orbitals with the same spin. Take note that S has only one orbit. P has 3 orbits. D has 5 orbits. And F has 7 orbits. Each orbit can only hold up to 2 electrons, which is represented by the up and down spin. Now let's try to get the electron configuration of lithium. Following the mnemonic device, we have 1s2, 2s1. 2 plus 1 equals 3. Next, the orbital diagram for lithium is this. Again, S has one orbit, so we have one orbit here, and another orbit for 2s1. Then, let's write the arrow following the Pauli's exclusion principle and Hans rule. We have 1, 2, 3. This is the orbital diagram for lithium. Another example is silicon. The electron configuration is 1s2, 2s2, 2p6, 3s2, 3p2. 2 plus 2 plus 6 plus 2 plus 2 equals 14. The orbital diagram would be like this. Again, S has one orbit, so we have one orbit here. Another orbit for 2s2, then 3 orbits for 2p6, 1 orbit for 3s2, and 3 orbits for 3p2. Then, let's write the arrows. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is the orbital diagram for silicon. Now that we have done the first step, let's proceed to the second step. In our example, lithium, the last in the electron configuration is 2s1. This will be our basis in getting the 4 quantum numbers, which will lead us to the third step. The first quantum number is the principal quantum number n. It corresponds to the energy level. This one is very easy because the first number is the n. Therefore, in our example, n is 2. Now let's look for L, or the angular momentum quantum number. L is describing the type of orbital. We have 4 different orbitals as mentioned earlier. These are the S, P, D, F. For S orbital, L value is always 0. For P orbitals, L value is 1. For D orbitals, the L value is 2. For F orbitals, L value is 3. In our example, we are looking for S orbital, specifically 2s orbital. That means that the L value is 0. The third quantum number is the magnetic quantum number represented as m sub L. This number describes the orbital within a sublevel. In an orbital, an electron can have an upspin or downspin. And so, every orbital can hold a maximum of 2 electrons. Consequently, its value depends on L, or the angular momentum quantum number. This means that m sub L is between negative L to L. So if L is 0, m sub L is 0. But if L is 1, that means m sub L would be a number between negative 1 and 1. So that could be negative 1, 0, and 1. Another example, let's say L is equals to 3. That means the m sub L would be a number between negative 3 and 3. So that would be negative 3, negative 2, negative 1, 0, 1, 2, 3. This expression shows the relationship between m sub L and L. So in our example, since the value of L is 0, thus m sub L is equal to 0. The last quantum number is the electron spin, or m sub s. It designates the direction of the electron spin and may have a spin of positive 1/2 represented by arrow up, or negative 1/2 represented by arrow down. This means that when m sub s is positive, electron has an upward spin, which can be referred to as spin up. When it is negative, the electron has a downward spin, so it is spin down. Given our example, it has a spin up. Thus, m sub s would be positive 1/2. Let's have another example. Find the 4 quantum numbers for neon. So the first step is write the electron configuration, and that is 1s2, 2s2, 2p6. The orbital diagram of neon is this. Since 2p6 is the last in the electron configuration, this will be our basis in getting the 4 quantum number. So n is equals to 2. Since it is p, therefore the value of L is 1. Since our L is 1, this means that our m sub L would be anything between negative 1 to 1. And that would be negative 1, 0, 1. Since the last arrow ends with 1, therefore m sub L is 1. And since it is a downspin, we have m sub s is negative 1/2. Now it's your turn to try. Grab your pen and paper. Identify the 4 quantum numbers of silicon. You have 1 minute to answer this. Let's check your answer. The electron configuration of silicon is 1s2, 2s2, 2p6, 3s2, 3p2. The orbital diagram will look like this. The last in the electron configuration is 3p2. So this is where we will base our 4 quantum numbers. N is equals to 3. Since this is on p orbital, L is equals to 1. Based on L, we have -1, 0, 1. The last spin ends up in 0. Therefore, m sub L is equals to 0. And since it is an upward spin, the m sub S is positive 1/2. Did you get it right? Great job, students! But wait, there's more. Did you know that through electron configuration, we can also determine the period number, group number, number of paired and unpaired electrons, and number of valence electron and core electrons? Yes, you heard it right. Period is a horizontal row of the periodic table. There are 7 periods in the periodic table, with each one begins from left to right. To find the period number, you have to write the electron configuration and get the maximum value of N, or the highest energy level. For example, neon has an electron configuration of 1s2, 2s2, 2p6. The maximum value of N is 2. Therefore, neon is in period 2. You can check the periodic table if that is correct. Another example is calcium-20 with an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. The maximum value of N is 4. Therefore, calcium is found on period 4 in the periodic table. Can you get the period number of silicon? You have 30 seconds. The answer is 3. Very good. Next, group number is a set of elements in column which have similar chemical and physical properties. There are 18 groups in periodic table. This periodic table is classified into 4 blocks: S, P, D, and F. It is completely based on the last electron. If it ends in S, then it belongs to the S block. If it ends in P, then it belongs to the P block. In order to find the group number, we need to follow the formula shown in the table. Going back to our example neon, since the last electron is in P, we are going to use the formula in the P block, wherein Ns plus Np plus 10. Let's substitute this. We get 2 plus 6 plus 10 equals 18. Therefore, neon is found on group 18. For calcium, the last electron is in S block, so we just simply count the number of electron of Ns, or the highest energy level, which is 4s. So, how many electrons does it have? 2. Therefore, calcium is found in group 2. Can you get the group number of silicon? You have 30 seconds. The group number of silicon is 14. Did you get it right? Great! Next is valence electron. Are those electrons found in the outermost shell or energy level of an atom? While core electrons are the electrons in an atom that are not valence electrons and do not participate in chemical bonding. For example, neon, the highest energy level of neon is 2. So we will add 2 plus 6, we have 8 valence electrons. And this one, we have 2 core electrons. Another example is calcium. The highest energy level is 4. Therefore, the valence electron is 2 and the core electrons is 18. Now, it's your turn. Find the valence electron and core electron of silicon. Your 30 seconds starts now. The valence electron is 4 and the core electron is 10. Are you correct? Great job! Lastly, unpaired electron is an electron that occupies an orbital singly rather than as part of electron pair. And paired electron is when 2 electrons occupies the same orbital in an atom or molecule. We can get the paired and unpaired electrons using the orbital diagram which we have discussed earlier. For example, neon. How many paired electrons does it have? 2, 4, 6, 8, 10. We have 10 paired electrons and there are no unpaired electrons. Now, your turn again. How many paired and unpaired electrons does silicon have? Correct! Silicon has 12 paired electrons and 2 unpaired electrons. Very good, grade 9 students! Here are the key points of our lesson today. Quantum mechanical model determines the energies an electron can have and shows the likely or probable locations of electrons around the nucleus. This model was proposed by three physicists, namely Louis de Broglie, Erwin Schrödinger, and Werner Heisenberg. There is a total of 4 quantum numbers used to completely describe the movement of each electron within an atom. These are principal quantum number n, angular momentum quantum number L, magnetic quantum number m sub L, and electron spin m sub s. Electron configuration and orbital diagram is necessary in finding the quantum number of the electrons. Now, let's answer some of your questions. Question 1. What is energy level? Energy level, or also known as electron shell, are fixed distances from the nucleus of an atom, where electrons may be found. Take for example Bohr's model. This is the first shell, or energy level. This is the second shell, or energy level. This is the third shell, or energy level. And this is the fourth shell. Second question, what is SPDF? Every energy level or shell has subshell or sublevel. These subshells are denoted by SPDF. They are orbitals or the regions of space in which electrons are most likely to be found. Take a look again at Bohr's model. The first shell has only one subshell S. The second shell has two subshells S and P. The third shell has three subshells S, P, D. While the fourth shell has four subshells S, P, D, and F. And like what we have discussed earlier, S has only 2 electrons. P has 6, D has 10, and F has 14. So, the first shell can only hold up to 2 electrons. The second shell can hold up to 8 electrons. The third shell can hold up to 18 electrons, and the fourth shell can hold up to 32 electrons. For further questions and clarifications, do not hesitate to ask your subject teacher so they could guide you in answering your activity sheets. This is Ma'am Cherry. I will see you again on another fun-filled discoveries in science.